Hello everyone, I am Ankit Barik. I'm a postdoctoral fellow at the Johns Hopkins University in Baltimore, Maryland, and I'm a member of the MAGPIE group here, which stands for Magnetism and Planetary Interiors. You can reach me through my email or by following me on Twitter. Today I'll talk a bit about global inertial modes and angular momentum transport associated with them. But before that, let me talk a bit about myself. I am a developer of a few different codes, the first of which is called Magic. It's a 3D anelastic MHD code for studying various different problems in rotating spherical shells. This is the code I used for my PhD as well, and this is the code I'm most familiar with. The second one is called Cori. It's an eigenvalue code. It's a 3D eigenvalue code for rotating spherical shells, and presently it can only handle incompressible fluids. There is a long-term plan for making it anelastic, but that's far in the future. Thirdly, the third goal, let me move myself away a bit. This is called Gamera. It's a 3D compressible MHD code for magnetospheric simulations, which I am somewhat familiar with, and I've modified some things on it. All right. Besides these, I have also written a couple of teaching tools. The first one is called InnerModZ. I don't know why I put the Z there, but it's a Python package to plot analytical inertial mode solutions in a full sphere. And the second one is called Planet MagFields. It's a Python package where all the planets in our solar system that have an active dynamo have taken the magnetic field data of them, put them all in one place, and written a package where you can sort of play around with that data and visualize it, even in 3D, extrapolate potential, and so on and so forth. And using these tools, this is the sort of research I do. I have a couple of projects going on fundamental fluid dynamics. The first one involves inertial waves. That's sort of what I did during my PhD, studying inertial waves in rotating spherical shells. As well as using the code Cori, I now also study onset of convection in rotating spherical shells. Besides fundamental fluid dynamics, I also like working on planetary dynamos. So currently I'm working on the dynamos of ancient moon, Mars, and gas giants. And lastly, I'm also foraying into work on planetary magnetospheres. Alright, now to the lecture part of my talk. So before talking about inertial modes and angular momentum transport, which is the later part of my talk, let me first sort of give an introductory talk on inertial oscillation, inertial waves. Now, to understand inertial oscillations, it's useful to sort of provide an analog with internal gravity waves, where if you have sort of a stable density stratification, and if you lift up a parcel of fluid against gravity, it falls down and then sort of rises up after it has overshot its equilibrium position, keeps going back and forth. Now, if you consider a fluid in solid body rotation, it has a sort of different kind of stratification. It's stratified in angular momentum. So if you want to take a fluid parcel and move it away from its position, by position I mean the distance from the axis. If you change it, it will want to go back and then start oscillating about the mean position. So these are called inertial oscillations. And what happens is, once you move it away, the centrifugal force, which is also the pressure gradient in the absence of any velocity, then pushes it back to its original position. But while moving back, the Coriolis force acts on it because we are in a rotating frame. And what happens is it makes the fluid parcel go in circles. And these motions are actually retrograde. They are opposite in the direction of the rotation axis. Now, if you construct a free body diagram of this parcel and write down the forces and so on, this is the equation of motion that comes up, where this is just a simple harmonic oscillator, and the oscillation frequency is given by twice the solid body rotation rate times sine of the angle that the particle makes, or the position vector of the particle makes. Now you can see that the magnitude of oscillation frequency then lies only between 0 and twice the solid body rotation rate. Now in a continuous medium, if you keep oscillating it, it will lead to oscillations first if you just oscillate it once, but then if you sustain that oscillation, it will lead to waves. And these waves are called inertial waves in a fluid rotating with solid body. Now if you perturb a fluid rotating with solid body with a velocity u and a pressure p, it will evolve according to the linear Navier-Stokes equation. So here we have gotten rid of the linear term and gotten rid of the viscosity, and that's the equation you get. Performing a bit of algebra gives you the wave equation from it, and you can substitute wave-like solutions to obtain first. If you can substitute this wave-like solution in the continuity equation first to obtain this result, which simply says that the velocity and wave vector are perpendicular to each other, so they are transverse waves. And substituting it in the wave equation gives you the dispersion relation, which shows again that the magnitude of frequency lies between 0 and twice the rotation rate. So this can only lie between 0 and 2 omega, and the frequency depends only on the direction of the wave and not on the magnitude of the wave vector. And you can see that this can be transformed into, this dot product can be written in terms of just cosine of the angle that the wave vector makes with the rotation axis. And so what you can see here, that this is a cosine, while in case of the particle you had a sine of the angle, which shows that the angle that the particle oscillation makes, or the particle displacement makes with the rotation axis, is actually complementary to the angle that the wave vector makes with the rotation axis, which lead to the same conclusion, that the velocity perturbations are perpendicular to the wave propagation direction. So these are transverse waves, just like on a string. And as we saw, the frequency of the waves lie between the magnitude lies between 0 and twice the rotation rate. The frequencies can lie between minus 2 omega to 2 omega. How do they look like? So these are sort of the wave fronts, and the arrows show fluid velocity, and this is the wave propagation direction given by k. And the phase velocity actually goes along these wave fronts, and you can see these velocities are in different phases. Right. However, the group velocity actually goes perpendicular to these, right? So they actually will travel perpendicular to perpendicular to the phase velocity, perpendicular to the direction in which the wave fronts are traveling. And each particle also moves in a circular path, as we saw for inertial oscillations. And time for a movie on inertial waves. So what you see here is that you see these arrows are in different positions all over. So this is where the phase is traveling. So that's making it oscillate, and that's making these particles go into inertial oscillations in different places. While you'll also see there is a different sort of almost wave-like envelope traveling in a perpendicular direction. So when these arrows face this way, these arrows face this way, and after a while, it's the other way around, right? So you can see these arrows are going round, and these arrows are following them, and then these arrows follow them, and so on. So there's a wave-like thing going in this direction as well. And that's the group velocity. So the phase velocity is going this way, and the group velocity is going that way. So that's the strange thing about inertial waves. Right, back from the movie, you see we can now start talking about global inertial modes. And the difference between waves and modes are basically, you can think about them in terms of a string. If you have a taut string, you can and let's say you have an infinite taut string somehow. You have a stretched out string infinite in length, and you can keep sending out wave pulses through it forever. But if you pin the two ends down and you then start to pluck it, like on a guitar, you'll set up standing waves, right? So once you set up standing waves, those then become these global modes. And the only difference, as you may have already realized, is that one obeys specific boundary conditions and one does not. So global modes need boundary conditions. And the boundary conditions for fluids are the boundary conditions for fluids in a container, I should say, are impenetrability. So usually you have a container that does not allow fluid to go out, and either you have a no slip boundary or a free slip boundary. These modes have special properties. So these modes are always orthogonal to each other. So you can take two modes and integrate over volume, you get a delta function. Their frequencies are also bounded by twice the rotation rate of the container. However, these frequencies are not continuous like the plane wave frequencies, where you had a cosine theta, so it could vary continuously anyway depending on direction. These are actually discrete. So you would actually have to solve for the modes that satisfy these boundary conditions, and they will not exist for every frequency out there. How do these modes look like? So the most relevant geometry for us is spherical, if you think of stars or even planets. And this is how these modes look like in a sphere. They can be analytically solved for in a sphere. There is no inner boundary in there, so there is no inner sphere, like there is no radiative or any zone in there. It's just a full sphere. And on the surface, their structure resembles a spherical harmonic, and that's how the notation is used as well. So this one is called the 5-2 mode because the velocities. So this is the cylindrically radial velocity perpendicular to the axis, and this is the zonal flow in the phi direction. They actually resemble the 5-2 spherical harmonic on the surface. Now, when you actually apply realistic boundary conditions and you introduce an inner sphere, you would start seeing these sort of ray-like structures, and what these are is places where the solution actually goes singular in the absence of viscosity. So the problem in general is mathematically ill-posed, and these are places of singularity. And in the presence of viscosity, these sort of form, because they can't be singular anymore, in the presence of viscosity, they form these internal free shear layers. And you can see their signature on a surface map as well. Moving on to Rossby waves. Now, Rossby waves satisfy more or less the same equation as inertial waves, and traditionally they have been analyzed using a local analysis, where basically what you do is you take a local coordinate system using x, y, and z, where z is along the radius, x is along longitude, y is along latitude, or rather against colatitude, so y is northwards. You take that, and what you do is you say that, okay, this because they're commonly, or because they were originally described for the atmosphere, and they're also seen in oceans, these layers are pretty thin. So you got to work with a thin layer approximation. So what is commonly done is that you ignore any flow in the radial direction or in the vertical direction. And then in the process, you also ignore the effect of the Coriolis force in that direction. So what it comes down to are these simplified equations, right? So you only have two-dimensional equations, and the Coriolis force now varies with latitude. Why? And then you can cross differentiate and so on and do a little bit of algebra and obtain what is known as what is the classic Rossby wave dispersion relation, using what is known as the beta plane approximation, where you assume the gradient of the of the local rotation rate along the latitude is beta. You can include the two or not, it's up to you. But the basic relation looks like that, and the negative sign points out that the wave pattern always travels westward, so it's retrograde, while the Earth is rotating eastward. You can also perform a global analysis of Rossby waves, or sometimes called planetary modes, so these are global modes. And if you stick to the same approximation that the radial flow vanishes, you find you can then write velocity as curl of a stream function, and then you can solve for the stream function, and you can expand it in spherical harmonics and obtain this dispersion relation using certain L and M of the stream function. However, some inertial modes, especially when the L and M of the inertial modes differ by 1, automatically satisfy the radial flow vanishing condition, and then you can obtain a slightly different dispersion relation of frequency dependent on M only now, because L is not independent anymore. And these are actually equivalent to these Rossby modes, at least to some of these Rossby modes that we saw earlier. Let me show you an example. So for example, the 3-2 inertial mode is equivalent to the 2-2 Rossby mode. So the indices are actually slightly different. And not every Rossby mode, because we are assuming from the get-go that the radial flow vanishes, not every Rossby mode will have a corresponding inertial mode. Now I come to the slightly more complex part of my talk, which is triadic resonances. So if you consider the Navier-Stokes equation and you push away the nonlinear term on the right hand side, keep in mind we are still in inviscid, and then we non-dimensionalize using a length scale, a time scale which is the rotational time scale, and a velocity scale, we would obtain an equation that looks like this with the Rossby number in front of the nonlinear term. Now the Rossby number, if the rotational effect is strong, will be small, so we can treat this as a small parameter and start expanding our solutions in Rossby numbers. And once you do that, at 0th order, you obtain the inertial mode equation. At first order, you obtain an equation that looks like that with the nonlinear term from the 0th order solution. Now, if the velocity of the 0th order, they consist of inertial modes. Now let's say that this velocity consists of 2 inertial modes, because we want to see the coupling between 2 modes. And once you write that down, with 2 inertial modes 1 and 2 with corresponding M and omega, as that's how they look like in spheres and spherical shells. You have the azimuthal wave number and the frequency, and you say that the first order velocity u1 varies as with m3 and omega 3. Now on the left hand side you get this exponent, on the right hand side you get that. Now imagine if this part in front, the factor in front of phi, matched with m3, and this part matched with omega 3, then that means this nonlinear interaction is actually directly feeding into a mode that can help u1 grow, right? So that leads to a condition for resonance, where you have m3 equals m1 plus minus m2, and omega 3 equals omega plus or minus omega 2. And these are called triadic resonances. Now think if u0, the 0th order solution, instead consists of just one mode, and there is a self interaction, out of that you can get out an m3 that's equal to 0, because m1 minus m2 will then m1 m2 will then be the same, and you'll get m3 equals 0, which means that it can actually feed into a zonal flow and generate a mean flow. And whenever you generate a mean flow, you get angular momentum transport. Now, I performed a couple of simulations where I artificially excited a Rossby wave-like inertial mode, which is easy to do by a simple so-called toroidal excitation. So m equals 2 will excite the 3-2 mode, which is the Rossby 2-2. M equals 3 will excite the 4-3 mode, which is the Rossby 3-3. And what I find is that when I excite, for example, a 3-2 mode, this is what it looks like. That's the zonal flow. And in profile, you can see that the zonal flow in a slice looks very much dominated by the inertial mode. However, if I take a mean, I still get a net flow out of that. So there is some amount of self-interaction going on, which is giving rise to a net zonal flow. Same is the case for the 4-3 mode. You can see there is a net zonal flow. However, if you notice the numbers, it's pretty weak. Now, how this angular momentum transport depends on different parameters is yet to be studied, but that's what I tried out. And the basic premise of this had already been shown by Andreas Tilgner back, I believe it's his 2007 paper, where he shows that you are supposed to get zonal flows, and you do, but a thorough study of this has not really been done. So in summary, inertial waves and modes are common waves in rotating fluids. And locally, Rossby waves are governed by the variation in Coriolis parameter. That's what they're governed by. You can also perform global analysis, and global Rossby modes, they have the unique feature of vanishing radial flow. That's the main approximation that goes in there. So they're also often known as toroidal modes, because there's very little radial flow. And inertial and Rossby modes can also potentially transport angular momentum through self-interaction. And these are my contact details. You can reach me anytime. And thank you very much.